So in this section, we're going to talk about inverse functions. There are two objectives. First one, determine whether a function is one-to-one, and if it is, find the formula for its inverse. So keep in mind, the only function for which inverse is possible is one-to-one function. That's the reason we need one-to-one function. And then eventually, this is the notation for inverse. If you try to find the composition of function and its inverse, what happens in both order? That's what we're going to do. So first of all, inverse means reverse. Let's say you have a function. It's a function or a relation. It doesn't matter actually. So if you have a relation or a function, it's going from A to 1 and B to 2, for example. This is just an example, okay? Inverse means instead of going from A to 1 or B to 2, so you have a relation A goes to 1 and B goes to 2. So instead of doing that, you flip it. You go back. You reverse it. That reversal process is inverse of the original relation or function. Okay? When we go from an output of a function back to its input, so this is the output and this is the input, and here we say function, but if it's not a function, that is also fine. We get an inverse relation. When the relation is a function, we have an inverse function. So let's say you have a function, and when you go back, you get a relation. Sometimes that relation is a function, sometimes it's not. If it's a function, that's called inverse function. Interchanging the first and second coordinate of each order pair in a relation produces the inverse relation. So like here, if you just switch x coordinate and y coordinate, then whatever relation you get, that's the inverse relation. Here is one example. Let's say you have a relation H, and these are the inputs and outputs. The inverse of this relation is you just switch x and y coordinate, and this is what you get. So if this is a function and then inverse of that function is also function, that's the inverse function. Interchanging the first and second coordinate of each order pair in a relation produces the inverse relation. Sometimes that might be a function. If a relation is defined by an equation, then you can find inverse. Interchanging the variable produces an equation of the relation. So let's look at one example here. This is the graph of x squared minus 5x. This is the graph of x squared minus 5x. You know, the same color. And if we reverse means the x coordinate will change to the y coordinate. So this x coordinate goes to the y coordinate of the reversal, and this y coordinate goes to the x coordinate of the reversal. When you switch them, this is the graph you're going to get. And if you look at the graph, you see that these two graphs are symmetric with respect to this line y equal to x. Symmetric means if you place the graph, and then if you draw this line, then you will be able to see that these are the mirror image of each other if you place the mirror on y equal to x line. The graph of a relation and its inverse are always a reflection of each other across the line y equal to x. Okay, so that's for the relation. So when it's possible, to get inverse function, to have an inverse function, your original function has to be one-to-one function. And what is one-to-one function? A function is one-to-one if for different inputs there are different outputs, or for different outputs, if two outputs are equal, then inputs must be equal. So only that function is called one-to-one function. And then we use very special type of notation for inverse. This is the notation f, and this notation is called f inverse. Here you have to keep in mind this sign -1 is not actually exponent. It's not exponent. This is not equal to 1 over f of x. That is completely different. This is just only for the notation purpose. Okay, f to the power -1 is not actually -1. This is just the notation for f inverse. Whenever you see this, just read this as f inverse. Okay, so if a function is 1-to-1, then its inverse is also a function, and that's called inverse function. The domain of a 1-to-1 function is now becomes the range of the inverse. So the domain becomes range becomes the domain, they just switch. A function that is increasing over its entire domain or is decreasing over its entire domain is 1-to-1 function. That's a very easy way to find out if something is either increasing or decreasing, then that's a 1-to-1 function. If you have a graph of a function, you can always tell either it's a 1-to-1 or not by using the horizontal line test. This test says, if you have a 1-to-1 function, the graph, then no horizontal line should cross the graph more than once. For example, this graph, this horizontal line is crossing more than once, so it's not 1-to-1 function. Okay, and when you try to plot its inverse, it's not even the function. So inverse is not a function. So you can use the horizontal line test to test either the function is 1-to-1 or not. If you want to find out the inverse for any function, given function, then these are the steps you can follow. I'm going to follow this step while doing some examples. First of all, you replace function by y, you interchange x and y, and you solve for y, and finally you give f inverse of x name for that y, which is the inverse. Okay, you can plot the graph of inverse. The graph of inverse, whenever you try to plot, it's just switching x and y coordinate. You can just switch the x and y coordinate of the original graph, and it's going to give you the graph of inverse. And keep in mind, the graph would be reflection of the graph of original function across the y equal to x. So if you have two inverse function, and if you try to find their composition, it's always going to be the same as an output is same as an input. Okay, no matter which order you take. So this is the test you can use to check either two function are inverse or not. Sometime you can restrict the domain of the original function to make it 1-to-1. For example, let's say this is the original function. When you try to find its inverse, the inverse would give you two different outputs. If you have two different outputs for one single input, that's not a function, so you cannot find the inverse function here. So what you can do, you can restrict your original function in a way that it's a 1-to-1. For example, this is the original function. If I restrict this function in the domain from 0 to infinity, so 0 to infinity means this would be the graph. That's now 1-to-1. And for this 1-to-1 function, I can find its inverse. So sometimes restricting a domain could help to define inverse function. Okay, let's look at some examples from this section. Find the inverse of the relation. This is the relation you have given. Inverse means just switch x and y coordinate. So the first point would be 2, 4. After switching x and y coordinate, the second one would be -6, -7. The third one would be -3, +8. +8, not the 9, okay? And the fourth one would be -5, +5. You just have to switch x and y coordinate. Is this a 1-to-1 function? This is actually cubic function. So cubic function is actually 1-to-1. Yes, the answer is yes. Is this 1-to-1? By looking the graph, it's yes, because it passes the horizontal line test. This is 1-to-1? No, because it does not passes the 1-to-1 the horizontal line test, so that's not the 1-to-1 function. What about the inverse of this? Just reverse it. Find the equation of the inverse relation for the following relation. So this is where we can use these steps for finding the inverse of any relation. You can just replace x and y. So in this problem, what I can do is, this is the original question, y equal 4x minus 5, and this is 1 to 1 because it's a straight line. Just replace y by x and x by y and solve for y. So when you solve for y, you bring this 5 to other side. So what would be the value of y? Y is x plus 5 divided by 4. So that's the inverse relation, inverse equation. So y equal x plus 5 divided by 4. That's the inverse relation. What happened? Did I x plus 5 divided by 4, x plus 5 divided by 4. The equation of the inverse relation is, oh, I forgot the y part. I forgot the y part. Y equal, that's the equation. So here is the thing, look at here. For this one, originally what we're doing, we're multiplying the inputs by 4 and subtracting 5. The reverse of that would be, we're adding 5 to the inputs and dividing by 4. Okay. Let's say another problem. Graph the inverse of the function, one-to-one function. Choose the correct graph on the right that shows the inverse as dashed line. So first of all, this is the graph and its inverse. Is that true? So you just have to see, are they reflection of each other when you pass through, when you draw y equal to x line. So you can do that. For example, let's find out a point. The point is this one, which is at 0, the graph has value -4. So at -4, the value is supposed to be 0, but it's not 0. You understand? So this is not the graph. What about this one? This looks symmetric at, for example, at 0, the value of the function is -4, but at -4, the value of the function is not 0, so that's not right. Where is that? This is also not right. Let me go back here. It looks right because at 0, it's almost -4, but not exactly -4. And at almost -4, it's 0, and it looks symmetric reflection across the y equal to x line. 2, 9, and 9, 2 should be on the graph of the inverse. This is not right. 2, 9, what is 2, 9? 2, 9, and 9, 2, 9, 2. Yeah, 9 supposed to have 2, but that's not the case, so I was wrong here. What about this one? At 2, this is almost 9, and at 9, it's almost negative. That is also not right. What about this one? One more time. At 2, it's almost 9, and at 9, it's almost 2. This is the right solution because it looks symmetric when you draw y equal to x line, and at 2 the value is almost 9, and at 9 the value is almost 2. Yes, so this is the right one. Let's try to do another one. For the following function, determine if it's a one-to-one or not. If it's one-to-one, find the inverse. This is the linear function. Linear function is always one-to-one, so it's a linear. So the answer is yes, it's a one-to-one. How do you find the inverse? Inverse means you just replace function by, using this approach, function by y, and then x by, and then you, let me just use a blank page here. Okay, so first of all, you just replace the function by y, and you write down that as an equation, And now you just switch y by x and x by y and solve for y. Finally, y is x minus 8. That would be the inverse function. So remember, it makes sense. In the original function, you're adding 8 to the input, and in the inverse, you are subtracting 8. You are going back. So you are subtracting 8 from the input. What about this? How do you find the inverse of this type of function? So one more time, write down the function as y, x plus 9 divided by x minus 2. Replace, switch y by x, and then x by y, and solve for y. So multiply both sides by y minus 2, and then distribute the x. And now bring all the y's to the left and all the x to the right. So I'm going to subtract y and add 2x. By doing that, this is gone, and here I have x minus 1 times y after factoring y. And here this is gone. It's a 2x plus 9. And the solving for y means divide both sides by x minus 1. So y would be 2x plus 9 divided by x minus 1. So the function is 1-to-1. Yes, always this type of function is 1-to-1 because it's a linear on the top and linear on the bottom. The inverse is, you need to solve like this, which is 2x plus 9 over x minus 1. 2x plus 9 over x minus 1. 2x plus 9 over x minus 1. You have to function, and then you like to check their composition. What is the composition? Let me you need to check the composition. Let's do that. So you have a function f and f inverse. So f inverse composition of f of x. This is finding the value of f inverse. Go to the f inverse and replace this x by the value of the function. That's the meaning of this. Go to this one, and wherever you see x, replace that x by the original value of the function, which is 2 over 9x. So if you simplify, that gives you x. Similarly, if you try to find f composite of f inverse x, find the value of the function at f inverse of x. So what do? You go to the original function and replace this x by the value of f inverse. So which is 2 over 9 times, you replace x by the everything here, 9 over 2x. And this gives you the same output. That's the reason the answer is yes. So to show that this f inverse of x, find this and check to see that only at least one is x, each is x. So both of them are x. Okay, that's all for this section.